Good morning, students. We had done few things in the current electricity. Welcome you again in this chapter, current electricity. Today we will do Kirchhoff's law. So let us quickly understand what is Kirchhoff's law. First rule of Kirchhoff's law is very simple. It is called Junction Rule. It is basically telling you the distribution of current. It is telling you about the distribution of current at any junction. So very quickly, if we try to understand, this is our junction, and if multiple wires are there, it is, at this junction multiple wires are joined, and there are 5 I have taken here, I1, I2. These two currents are entering the junction, and then these 3 currents, 3, I4 and I5, are leaving the junction. Then what will happen? I5, I1 and I2 are entering the junction. This is the junction. I3, I4 and I5 are leaving the junction. These are the currents. Currents entering the junction equals current leaving the junction. So basically this is how the statement is. The sum of the currents entering the junction is equal to the sum of currents leaving the junction. So this is very simple. Here what we need to know is that currents entering the junction is taken to be positive. I will explain you why this is happening. Focus on this. As per this statement, this is there. Now if we take it into the in this manner, we will say that I1 plus I2 plus this will be minus I3, minus I3, minus I4, minus I5, this equals 0, right? As per this, as per the statement, what is there? Current entering is algebraic sum of current entering is I1 plus I2. Algebraic sum of current leaving the junction, I3 plus I4 plus I5. Now what we will do? We will make this one equation, right? Bring all of them together. So I1 plus I2 minus I3 minus I4 minus I5. So this is equal to 0. So in other words, the same thing can be stated as summation. Algebraic sum of all the currents at any junction is 0. Algebraic sum of all the currents at any junction is 0. This is what we can interpret. This is what we can conclude, right? Okay, one more thing here we need to understand. Here we need to understand is that I3 is taken minus, I4 is taken minus, I5 is taken minus. So can we conclude now that current entering, this is negative current when leaving the junction, when leaving the junction, leaving the junction, right? Positive when current entering the junction. Can we say that? Entering the junction, right? So it is very simple. At any junction, net current equals 0. So current entering is taken to be positive, current leaving the junction is taken to be negative. So isn't it very simple? Now let us move on. One more basic idea behind this. First of all, on what principle this rule is based upon? This rule is based upon principle of conservation of energy, conservation of charge. This rule is based upon principle of conservation of charge. So junction rule is based upon conservation of charge. This is one important information that we need to keep in mind. At times in CBSE they can ask you, show that junction rule is based upon principle of conservation of charge. How is this possible? Can we say that? Yes, we can. This is the statement of the law. As per the statement, this we can put. So we know that current is rate of flow of charge. So what we can do? All the charge entering the junction equals all the charge leaving the junction. That way we can conclude that, okay, fine. The net charge entering equals net charge leaving. That means it is following the conservation of charge. Right? Now, let us move quickly to the next rule, and that is very simple. That is very simple. What is it? So let us understand what is happening in this. Suppose you have got a circuit, a complete loop, a circuit. I am taking one circuit consisting of resistor, some of one cell I have taken, another resistor I have taken. This is R1, this is R2, and then again let's put one more cell. Okay. So this is the circuit. This is the closed loop, right? So A, B, C and D. As per the statement of the law, inside the closed loop, potential difference, algebraic sum of potential difference of all the components. What are the components I have taken? I have taken this component, potential difference across this, potential difference across this, potential difference across this, plus potential difference across this. Potential difference of all the component across all the components consisting of cells, resistors, whatsoever, is 0. What is the law mathematically saying? This equals 0. Algebraic sum, or you can say algebraic sum of changes in potential. Changes in potential means potential difference or potential drop. That would make the same meaning, right? Potential around any closed loop involving resistors and cells in the loop is 0. In the loop. So we need to understand this closed loop. So what did we observe here? Potential difference of this plus this plus this plus this. Inside the loop, in a closed loop, net potential difference, algebraic sum of potential difference is 0. So individually we need to measure the potential difference across each of the electrical component connected inside the loop. Right? So we need to understand in junction rule, as we looked into sign convention, we need to look into the sign convention in this rule as well. So far you are aware that, okay, potential difference across the resistor is I into R from Ohm's law. Potential difference across a cell, if cell has got some internal resistance, then it is going to be EMF minus IR. If cell is being discharged, that means current is drawn from the cell, right? If cell is being charged, then EMF plus IR, that would be the terminal potential difference across the cell. So in this manner, you need to think of, suppose this circuit would contain a capacitor also. So in that condition, you need to take the potential difference across the capacitor, and algebraic sum of all the potential difference would be 0. This is what this loop rule is saying, right? So before we move ahead to apply the law, we need to understand in a very systematic manner how sign convention is taken. Before I discuss that sign convention, I would like to tell you that maybe you would find in some other book something different. There are two ways to do that. I'll tell you why that is important. At times in some of the books, when you move from A to B, just pay close attention to this circuit. Pay close attention to this circuit. If inside the circuit, if you look at it, what is there? I am removing this resistor, potential difference across the resistor, potential difference across the cell. But we need to look into this resistor and then cell. This is R1, this is R2. Right? This is positive terminal, this is negative terminal, this is positive. This is EMF 1, this is EMF 2. I am not taking, or you may take this internal resistance as well. Let's say internal resistance is also there. So I will tell you why both ways are equal. What both way? Just pay close attention to this. As per our sign convention, one of the sign convention is this 1 and 2. Here if we take potential difference, just have a look. I have drawn it in this manner. See, if inside the loop you are going from A to B, if you are going from A to B, and that is the direction of current, in this direction from A to B, current is also flowing, and you are also traversing in the loop, because what will happen inside the loop, as you would say that okay, this is resistor, this is another cell, and this is another resistor, like this. This is A, this is B, this is C, this is D. So you have a choice. What choice? You can move inside the loop as A to B, B to C, C to D, and then D to A. That means loop is A, B, C, D, A. This could be the loop, or inside this you may move in this manner also, A, D, C, B, A. This is also the loop, right? So in one case you are moving from A to B, in another case you are moving from A to D to C to B to A, right? Clockwise and anti-clockwise. That is your choice. No one is going to ask you why you used that one, why you have taken that path. So that is your choice. You may choose as per your convenience, whatever, right? But what you need to understand is, during the journey from A to B, if negative terminal of the cell comes first, if the negative terminal of the cell comes first, you need to consider the value of EMF to be positive. This is what you have to understand. This is what you have to understand. VAB, this is positive. This is positive EMF, right? If you are moving from, while going from A to B, and your negative terminal of the cell comes first, you have to take plus C, plus EMF. Now, if you are going from A to B and you come across positive terminal of the cell first, then what you need to do? You need to take it negative EMF. This is one thing, this is one way. You can take the other way also. But I will talk about that. First of all, try to understand this sign convention. I will tell you why both are equivalent. There is no problem with any of the two methods. But I would prefer, I would encourage you to take this, because it has got very little logic behind it. And that logic also I'll tell you. Before that, let us talk about the potential difference across the resistor. So two cases, while traversing, you are traversing in the direction of current. If you are traversing in the direction of current, current moves from higher potential to lower potential. Potential drop is there. So you need to take it minus IR. If you are traversing, while traversing from A to B, you are traversing opposite to the direction of current. You need to take plus IR. You need to take plus IR. This is what you need to understand. This is method 1. If you will complete the loop, inside the loop, if you will take that, you will find that either way it is okay. Because ultimately, adding all the potential differences inside the loop, how many components are there? Okay. Across each component, you will find out the potential difference and add them all. What you will get? You will get the algebraic sum to be equal to 0. Okay, one more thing I would like to tell you, that in layman's language, you can put this thing in your mind that okay, cell is providing energy. So cell is the supplier of energy and resistor is the consumer of energy. Inside the loop, considering cells and resistors, total energy supplied by the supplier equals total energy consumed by the consumer. One is consuming the energy. The resistors are consuming. Cells are providing the energy. You must be aware of this, that when you say potential difference is nothing but work per unit charge. While knowing the definition about the definition of EMF, you had this thing. What? Inside the closed loop, EMF equals work done in taking a charge, unit positive charge, once in a closed circuit. That is one of the definitions, right? So basically, V, that is IR term, is nothing but the energy per unit charge. So you can consider it in this manner as well. What this is, the cell is supplying the energy and resistors are consuming the energy, supplying the energy and consuming the energy. Energy supplied equals energy consumed. Inside the loop, that is what you need to take into account. Is that okay? So now let us move on to this. We will take this question. We will take this question, we will do it. If you talk about the other method, you may switch it also. If you are going from negative to positive, you may take it positive, but this will be changed. And in that manner again, if you will add for the entire loop, result would be same. Result would be same. So now let us quickly understand how these two laws, using this sign convention, is used in a given problem. So we will take one question from NCERT itself. Let us see that. You must have seen this question. Right now what we will do, we will understand two things. One, junction rule, how to apply junction rule. Second, we will look into how to apply loop rule, right? And applying the loop rule, if you have got 3 loops, then 3 equations you will get. And if you get 3 equations, you have unknowns, you can find out the unknown values. I am quite sure that you are good in solving simultaneous equations. And this is what we will use here. So first of all, try to understand how to distribute the current. How to distribute the current. How to talk about the current inside the circuit. So let us take this example. First of all, what you need to do is take the cell. see where the cell is. Okay, you have got this one cell here, you have got one cell here. So what we can do, we will start from the positive terminal of the cell, one current. Let's call this current to be I1. I1 is the current from this cell. Cell has got EMF 10 volts. Okay. Now here at point A, if I2 is going in this direction, then in this direction, what was coming in? I1 was coming. So it will be I1 minus I2. I1 minus I2. This is the junction rule. What is happening? At this point A, what is coming? I1 is coming from this cell. From this cell. There is a cell here. From this cell, I1 is coming. I2 is leaving. What would be remaining would be flowing into this branch. This resistor has got 4 ohm value. Okay, this will come here till D, point D. Now, when this 4 ohm resistor has this current I2 coming in, this I2 till here is coming. Okay, fine. Now, I have used I1, I have used I2. Now let us talk about another current. So which current? This EMF of 5 volts from this cell of 5 ohm is sending I3 current here in this branch, and it comes till point B. Now what is happening? So I2 is coming, this is I2, this is I3, so it is for sure that in this resistor of 2 ohm, this I1 plus I2 current will be flowing. In this, across BC, I1 plus I2 will be flowing. Now, from C to D, if you look into what current is coming in, this I1 minus I2, okay, I1 minus I2. From this, I1 plus I2 current is coming. From this, I1 minus I2, and I2 is living in this. This is I3, sorry. This is I3. So, what current would be coming here? Here, this is I2 plus I3. This is I2 plus I3. Wait. In this circuit, I2 plus I3 is coming. In this 2 ohm resistor, I2 plus I3. I2 and I3. These two were coming in this. Right? Now, in this branch, what will happen? This is coming, and from this I2 plus I3, and this is I1. Because in this cell, I1 has started, so on the negative side of this, I1 will again enter. This is what we need to understand. This is 1 ohm resistor. This is 1 ohm resistor. This is 4 ohm resistor. So what will happen? I2 plus I3 minus I1 would be here in this 2 ohm again. Across CD, 2 ohm resistor, I2 plus I3 minus I1. So this was the distribution of current. One caution. If you have taken direction of current in a particular manner, let's say you have taken it from A to B, and suppose you got, when you worked out, when you got the value in negative. That means your assumed direction of current has got the opposite direction. You have assumed the flow of current in this direction from A to B. When you get the value in negative, that means that inside the circuit it will flow in the reverse direction. So nothing to worry about. You may take whatever direction of current. Make sure that current from the cell, if it is starting from one terminal, if suppose you are saying, okay, from this I1 is leaving, so on the from the positive side, from the positive terminal, I1 is leaving, that means I2 must be entering the negative terminal of the cell. This is what we need to understand, right? So here I have taken that particular thing, 10 volts EMF, this cell has got negative terminal in this, I1 has started, so I1 has to come here. So from here I2 plus I3, and in this I2 plus I3 minus I1, current will be flowing in this 2 ohm resistor across CD. So question is, we need to determine the current in each branch of the network shown. You know what we need to do? We need to apply, we have already applied what? We have already applied the junction law, junction rule. Now we need to apply what? We need to apply the loop rule. How to go about it? Let us take the loop. Let us talk about this. A, D, C, A. Loop A, D, C, A. This is loop A, D, C, A. Now another loop A, D, C, A we have taken. Now A, C, D, A. A, C, B, A. A, C, B, A. Third loop we will say. Third loop is what? Name the loop of this. B, C, D. Let's call this E and F. B, C, D, E, F, B. Loop B, C, D, E, F, B. These are the 3 loops. And inside the 3 loops, we will just add all the potential differences, and that we will put equal to 0 in the 3 equations. We will work out the values of 3 unknowns, I1, I2 and I3, and then it is easier. So let us move to find out what loop AC loop ACDA. This was the first loop. So see what is happening. ADCA, sorry, ADCA. I have taken the loop ADCA. ADCA. Just take the loop. ADCA. So from A to D, what current? This is the current. What potential difference? What is the resistor? So in the direction we are moving. See, direction of current is from A to D, and we are also traversing in the direction A to D, right? So what we will do? We will consider minus I1 minus I2, minus of I1 minus I2. This is minus 4 of this, right? Potential difference across this resistor is 4 into this current. But this has to be minus as per our sign convention. As per our sign convention, potential in the direction of current, potential difference across the resistor is minus IR. That is what we are doing. Okay. So this from A to D we have already taken. From D to C, this is the direction of, this is the amount of current. What? And this is resistor. I2 plus I3 minus. So this is the direction of current. Here, this is the direction. So we are traversing from D to C. We are traversing opposite to the direction of current. Taking while traversing opposite to the direction of current, we need to take the potential difference to be positive IR. So what is the current here? Net current is I2 plus I3 minus I1 into 2. So I2 plus I3 minus I1 into 2, right? This is 2 resistor. Now From C to A, we have this resistor 1 ohm. What is the potential difference across this? Current is I1 and resistor is this. So we are again moving in the direction I1 into 1. I1 into 1. Now, we come across, while moving from C to A, we are moving from, while moving from C to A, what we are coming across? We are coming across negative terminal of the cell first. So if we come across negative terminal of the cell first, then what? We need to take the value of EMF to be positive. So this is what we will do. So we will do this plus 10. This equals 0. So is that okay? Pay close attention quickly. What we did, we have taken A, D, C, A. While traversing from A to D, we have this resistor of 4 ohm. Current flowing in that resistor is I1 minus I2. Potential difference in the direction of current will be negative IR. So current is I1 minus I2 into 4 ohm. So this is what? Minus 4 of I1 minus I2. Okay, this we did. Now from D to C, current across this 2 ohm resistor is I2 plus I3 minus I1. We are traversing opposite to the direction of current. When we are traversing opposite to the direction of current, we have to take plus positive plus IR. Positive IR. So current is I2 plus I3 minus I1 into 2. 2 is resistor. So this we have taken positive, right? Now from C to A, this is the current. We are traversing in the direction of current, so it is negative IR, right? Current is I1, resistor is of 1 ohm. So I1 into 1, and then negative terminal of the cell comes first. That would be positive EMF. So if EMF value is 10 volts. So that's what we have taken. So what we have taken, potential difference across each of the component, cell or resistor, whatever it is, we have taken, and then that we put equal to 0. Sum of the potential difference across each of the component equals 0. This is what we have done. So this is loop 1. Now you can solve this. You can make it simpler, right? You can make it simpler. Let us do this. Minus 4I1. Okay. Here you have again minus 2I1. Here also minus I1. Right? We have taken this. Now you have minus of minus plus 4I2. Plus 4I2 plus 2I2, right, plus 2I3 plus 10 equals 0. This is what you are getting, right? So ultimately what you are getting, this comes out to be minus 7I, minus 7I1 plus 6I2 plus 2I3 equals 10. This is, yeah, plus 10 equals 0. So this is our equation 1. This we can call as equation 1. Right? Now we will take loop, another loop, and we'll talk about that. What is the another loop? ACBA. ACBA. Now while going from this, from A to C, we come across positive terminal of the cell first. So let us put here this loop, this. Now loop ACBA. So minus 10 across this, minus 10 opposite to the direction of current, plus IR. This is plus I1 into 1. From C to B, we have we are moving opposite to the direction of current. So 2 of plus 2 of I2 plus I3, I2 plus I3. Then what? Let us see. Opposite to the direction of current. Again we are saying we are traversing from B to C, B to A, opposite to the direction of current, so 4I2. This is plus 4I2. This equals 0. So this was another equation. You can simplify that. And the third loop, and next we have third loop. Third loop is this. B, C, D, E. B, C, D, E, F, B. So first component is this, in the direction of current. So in the direction of current, what we have to take? What we have to take? I2 plus I3 minus 2I2 plus I3 minus 2I2 plus I3. Then you have minus again minus 2 of I2 plus I3 minus I1. From D to E, nothing. E to F, you have, this is minus terminal, this is plus. So this is plus 5 volt. Negative terminal comes first, plus 5 volt. Then what? Then comes, is there any resistor? No. From F to B, there is no resistor. So 3 terms are there. 1, 2 and 3. It has got no internal resistance, so we will not look into that. This cell also has no internal resistance. We will not talk about that. So this term plus potential difference of this equals 0. This was the loop. What was the name of the loop? B, C, D, E, F, B. Third loop. B, C, D, E, F, B. So you got 3 equations, 3 loops. What you need to do is you just solve this simultaneous equation and you will find out the value of 3 unknowns, I1, I2 and I3, and then your problem will be solved. So quickly, what we did today, we have understood Kirchhoff's law, we understood how to apply Kirchhoff's law. In the next session, we will talk about Wheatstone bridge and how unknown resistance using the concept of balanced Wheatstone bridge is determined. We will look into that. So thanks a lot. We will meet on the next session. Thank you.